All right, so oops. Make sure the video is, yep. All right, we're live now. It's being recorded, and that way we'll have a video of it. Okay, so we're in this class. So what I've done since last week is that I did post the lecture videos. So these are the videos that I recorded while I was talking last week, and I also posted the lab for both last week and this week. Lab 1 was a completely new lab, and we actually did a lot of what I intended to do during the presentation, but so I didn't quite finish the lab, but I cut it off. So there are 9 questions for you to answer. You can either answer them you can either submit them as a zipped up file, like a Word document, or there'll be a place to just enter text. There is a place, when you log in, you can see it for entering Lab 1. And then Lab 2 is today's assignment, and it will require you to upload some files. So you're going to be submitting some uploaded files. And from now on, the labs aren't a complete rewrite. I just need to rewrite them for using ArcGIS Pro rather than ArcMap. So they'll go up there faster. Okay. I will be, during my lecture, I will be utilizing the slides, but also I'll be going back and using ArcGIS Pro to demonstrate a concept. And so if you get ArcGIS Pro working on your computer and you want to follow, you can. It's not necessary to follow along during the lectures, but you certainly can. And then I realized that for ArcGIS Pro, you don't actually need to get an email from me. You just need to get the software, and then you can log in with the username and password that you set up last week in class. So if you go to the announcements here, there's a link right here to download ArcGIS Pro rather than send everybody an individual email. So that's what I meant there. You can click this link, and it should take you to it'll take you to this, and click download. And once you do that, you'll have the software that you need to install ArcGIS Pro. And so, as I mentioned last week, is there still somebody that wants ArcMap? I can send ArcMap codes. Okay, so yeah, if you need ArcGIS Pro, that's how you get it, and you log in with your ESRI account. Okay. Yeah. And it worked. Great. Good. Yeah. So you can also use, because I sent you a link directly from ESRI. ArcGIS Pro on your computer? Okay. Sorry, I'll learn everybody's names eventually. What's your name? Roy? Okay, so I'm going to look at ArcGIS online, and that's how I license ArcGIS Pro. License it a little bit differently, and I can see what the problem might be here real quick. Members. I don't see you. Yeah, you're right. Okay. Did you get an invitation last week? Did I even send you an invitation? Okay. Oh, I missed you. I'm sorry. Okay. So just tell me that information right now. We'll just do it. New member. What's the email address? CRRR. Like that? Okay. Yep, that's what we need as a user. Next. Next. Okay, so check your email and see if you got it. Everybody up there, did you get the software working, Mark? And I guess Mark was the only one up there that needed to get it working.
Yep, I'm good.
Okay, good. You got it? You got it? So now you sign up, and there's one other step I need to do after you sign up to give you ESRI access. So just let me know when you actually create your ESRI user account. And I can do that during the break. Okay. Actually, yeah. All right, so we're on lecture 2 here today. Now, some of the readings that I've given you actually pertain to the next couple of weeks. So there won't be as many readings listed next week as there has been. All right, so we're going to continue our discussion about cartographic modeling, map algebra. Map algebra and cartographic modeling are very, very, very similar. So cartographic modeling is this technique where we can think about the analysis that we're going to run, and we can set it up kind of like a flow chart. What enables us to do that is this concept of map algebra, where we have a formula that involves maps. So we have map A plus map B, maybe. That's a very simple formula, equals map C, or the output. So we could generalize that to say output equals some function of some other maps. Remember we talked about that a little bit last week. Okay. So last week we talked a lot about models and how raster data is really just a model of the real world. And all of those cells with numbers in them, those numbers represent some real world value, some value from the real world. It's a simplified version of the real world, but all those numbers represent some variable that exists. And it can either be an abstract variable, like we talked about population density, or it could be something that actually exists that we could visualize, like we could see, like elevation, or actually the color of the earth at that point, which would be an image. So today, we're going to move on, and the real power of GIS is we can take these models, these scale models of the world that we've stored on our computer, and we can take those models and then start to model what we call a process. So what's a process? Okay. Well, one simple process that I like to think of is think about how vegetation grows on the earth, right? Does vegetation grow the same everywhere? Like if we just left a plot of land open in Mississippi, I'm getting very big scale here. In Mississippi versus a plot of land in Arizona open, there's a difference, right? What explains some of those differences in how plants grow there versus here? Soil type, yeah, the soils are different. Yeah, there's different degrees of moisture. Temperature, yeah, temperature's a little different. I mean, still get pretty warm here, but yeah, the climate and the weather, exactly. So the process of how plants grow can be explained by other elements, and those other elements themselves can be scale models. So we can have a layer that represents temperature and soil type and elevation or whatever we think explains vegetation, and then we can actually model the process of, another way to say this is we can predict the nature of the plants there. We could do this on a totally different scale, right? We could also just think in Mississippi, what type of different plants might we see, near a river stream? Okay, near is a geographic construct, right? Like it's a measurement of how close we are to something. So we're going to see different vegetation types near a stream than we are in the uplands. In the uplands, at least, maybe it's a little bit different in Hattiesburg than here, but this is still kind of piney as long as you get away from the coast, right? So you get away from the coast, the uplands are mostly pines, a little bit of other things, and the areas right near the river, or the stream, are mixed, and that's because you get different types of vegetation. So that's a process. There are different types of processes out there that explain why things happen. And some of them have to do with how we treat the land or how humans interact with land. Some of them have to do with climate. But all of those things we could simplify and take and abstract the real world and try to build a process model that explains what's going on. That actually forms the basis of a lot of analysis. Really, what we're trying to do is create a process model to predict something, or to find something out, or to discover something new. So we've got spatial process models. Mostly, we're going to be concerned with spatial process models. There are models about the real world that aren't necessarily spatial in nature, but we're going to focus on those that are the function of maps. Okay, so we got our real world process, got our process model, and then that's going to be a representation of a real world process. Should have put that. Okay. So how does that get implemented in a GIS? Well, that gets implemented in a GIS through this map algebra, and we showed this slide last week. So map algebra is the process that we use, and we can either chain these together and make a very complicated formula, or we can execute the commands individually in order to chain them together, making the output of one. I'm going to hit escape here, and I think you all can still see it like this just fine. This way I can point with the pointer on here. So the output of one function, map algebra function, could be the input of the next one. There's lots of reasons why we might want to create spatial process models. I kind of stumbled through this a few seconds ago, but here it is presented on a slide. We might want to make a decision about actions. So this is what I was talking about before. We might want to know how much of something is going to occur, or where something is going to occur, or what's the best place to put something. Okay, those are all pragmatic reasons to create spatial process models. The other reason that we create a model is to actually better understand the process itself, to break down the process into its constituent components, and then we're testing, is this an acceptable model? Does this actually predict what really happened? And if it does, then we're saying, okay, well, if we can explain where certain vegetation grows based on temperature, soil type, and whatever, then it naturally follows that the logical extension of that is that those things influence the vegetation type, or at least they're related. Sometimes we actually find out that it's the opposite relationship, right? That they're actually related, but in the opposite way. So I showed this slide also in my my course last semester here, but oftentimes when we model a spatial process, it requires understanding a spatial relationship that it's more than just finding out what's there and what else is there. Sometimes it involves, that's co-location. What's there and what else is there? And does the fact that 2 things there or 3 things there or 10 things there together influence the spatial process we're trying to predict? Okay, that's co-location. But what happens if thing A is close to thing B, or they don't exist in the exact same place, but they're nearby? That would be distance and direction, or adjacency. Sometimes maybe I should have made these like indentions, but sometimes we refer to that as neighborhoods. Okay, what's in the neighborhood? And we'll talk about that a bit more next week when we talk about neighborhood operations. Probably a little more complex, and something that we don't cover in this class as much, is what happens if there's big differences in the way that things are spread over the landscape. Some things they exist and they change slowly over the landscape, and some things exist kind of like in a patchwork quilt, where there's lots of differences in how they look. So we could also try to study the way that the landscape looks. Another way to say this might be the texture of the particular data set that we're looking at. All right. Here's a couple of concepts that would be important to looking at spatial relationships. Tobler's first law of geography is that all things are related, but nearby things are more related than distant things. We implemented this in a few different ways in the vector course, but in this course, the main concept that we're going to talk about that is really related to this concept is spatial interpolation. When we talk about spatial interpolation, oftentimes we want to create a raster data set, but we only have point values. And so what if we want to take a number of point values and we want to predict the raster cells that would be in between all those point values? We just want to make an evenly spaced grid of values. That's spatial interpolation, and it involves measuring this relationship. Are things near each other really more related than things that are far away, or is it more of a patchwork where we almost have a random or a dispersed values? If you think about elevation typically changes fairly gradually, right? Especially around here. Okay. So the further you get away, the less related elevation values are. Temperature is also like that. You rarely see an abrupt change in temperature. When you do, it's usually called what? What's an abrupt change of temperature called? A front, right? Yeah, so we've got a cold front or a warm front or a cold front coming in, and that's what we call that. And so at different scales, we're going to have different degrees of how much things are changing in space. And also at different scales, we might have a very random pattern to our raster data set, or we might have a very predictable pattern to our raster data set. And so it's important to be able to quantify if our data set is random, or if it's dispersed, or if it's random, dispersed, or if it's clustered, yeah. Or in raster, it's more often not clustered, it's smoothly varying, which is another similar to clustered. But anyway, we talked about that a bit last semester in terms of making judgments, but now we're going to be talking about how that plays into spatial interpolation. I know not everybody was in the class last semester, so We're going to include that in our lecture that comes up. I think that's halfway through this semester. Okay. But we still have these concepts that have to do with at different scales. We're going to have different measurements of how things change in terms of space. And we refer to these two different problems as the modifiable aerial unit problem, or MOP, which means that that at different scales we may get a different answer on whether things have what pattern they have. The spatial pattern that's evident might be different at different scales. That's a summary of the modifiable aerial unit problem. The ecological fallacy probably should have been first, and that is that conclusions drawn at one scale don't necessarily hold up at another scale. All right. Models. We can do models a priori, meaning that we can use a process model, or we can create a process model for a body of theory that has been yet to be established. This would fall into the category of helping us to understand it better. And a posteriori, which is to explore an established theory. So one of the examples that I like to use a lot, I think I included it as a slide. No, I didn't. Oh, here it is. One of the models that I like to include a lot. I did this on my, 15 years ago on my doctoral dissertation. I looked at runoff in certain areas and the effect of modeling runoff using different resolutions, different scales. So runoff is something that's pretty well understood, and we can model how much runoff is going to occur. This is something that we're gonna work off based on this thing called a curve number, which is really a number that is telling us how rough the surface is. It's a function of the slope and the land cover and the slope, the land cover. Oh, that might be it. But anyway, the curve number, we can think of that as a value that changes geographically in space. So we can come up with an equation that allows us to predict how much water will run off of a certain area given a certain level of input. So if it receives 2 meters of rain, that's a lot. 2 feet of rain, that's still a lot. How much of that is going to flow off of that cell? So we can come up with a mathematical model to understand that process. And that would be a model that explores an established theory. Yep. This slide should have been there last week because we talked about scale models last week. But all right. So one of the powerful things about ArcGIS is it allows us to create models. We're going to do this today. It allows us to create models. We actually did a little bit last week in that new format that's called a raster function chain. So it's kind of like the newer version of Model Builder. But today we're going to actually use Model Builder specifically, and then later we'll continue to explore the function chains because I think I like them better. I think there's a reason that ArcGIS put them in because in a lot of ways they are superior to the old Model Builder. But a conceptual model is the ability to connect different processes together, and we can do that in ArcGIS. We can connect the different processes that maybe are included in an overall model. So here's a very generalized model of the water cycle. But if we wanted to model this, we could do that in a GIS with Model Builder using a graphical flow chart. That's what Model Builder allows us to do. So I showed that before. Mathematical model. Typically, almost always in the raster analysis workflow, we need to construct what we want to do mathematically before we actually do it. And then put it graphically, and finally we implement it. Now, mathematical models can be what we call deterministic. Most of the ones that we're going to do in this class are deterministic, but we are going to get toward the end, we're going to get stochastic models. The difference there is that if you have a model like this is a deterministic model, where the runoff equation, you'll always get the same value output when you input the same set of inputs. So when the curved numbers are the same and the P, which is the precipitation, when the curved number of the precipitations are the same, the output will always be the same value. Okay? It's like a normal formula. Lots of times we have things like that. However, in the real world, sometimes there are a process is so complex that we don't understand every single thing that goes into that process actually happening. And so one way to capture that uncertainty is to use probabilities. So we can modify this formula so that these values here, I'll point them out here so people up in Hattiesburg can see. These values here, this 0.02 or this 1,000 value, instead of always using the same number, we give it a random number in a certain range. And that would make it a stochastic model so that we could try to capture some of the variability that actually occurs in real life. Now, we'd have to have a reason for doing that. And we'd have to kind of understand and know in nature what the real range of values, the output values were if we were going to do this. Okay? But it is a very common technique that's used is to create a stochastic model using probabilities as inputs rather than simply hard numbers. Okay? And sometimes it allows us to give a range of possible values. Another way to do that is to use a simple deterministic model, but then report a confidence range, or an error set. So how are mathematical models created? For example, how did this mathematical model come up? How did we get that? Well, there are a few ways that happens. One is that they can be created empirically. So we go out and we actually observe. We find a watershed that has a certain characteristic, has a certain slope to it and a certain land cover to it, and we observe, well, it rained this much and we got this much water off, and we can do that a bunch of times and then use that to come up with a mathematical model. One tool for that is regression. Another tool for that is called simulation. The other way to do it is to theoretically construct a model built on existing mathematical models. So if we understand the actual physics of the process, for example, with reflected light, okay, we understand how much light is reflected typically from a particular surface, then we can create a model and use that mathematical model to then say, okay, do we see other, if we find out what in the lab, or we understand physically how much light energy is going to be reflected off of a certain type of soil that's exposed, then we can use that information to find out where all those other exposed areas are. Okay, now all the different types of models that I discussed are not mutually exclusive. They can be, you can have a graphical model that's also a mathematical model. And the take home here, what type of process models can be modeled in GIS? The answer is that they have to have a spatial component. Basically, specifically to this class, we need a data set, a raster data set that models the elements that are important to that process in order to create that model. I just turned you all down in Hattiesburg because you're a little bit, there's a little bit of feedback. So just talk loud and I can turn you up if you have a question. Okay. All right, so I think we've covered this slide pretty well. It's kind of the sum up slide. We can categorize, you should have gotten this from the reading. We can categorize all the functions that are available in raster GIS operations into 3, or sometimes we think of it as 4 different categories. So today we're going to talk about the first category. Okay? The first category are local functions. So the key to understanding raster data sets and understanding raster functions is to understand what values are stored in the cells that are trying to model a particular layer. So with elevation, the values stored in there are trying to model the height above sea level or above some datum. With temperature, they're trying to store the temperature value at that particular location, usually at a particular time. Okay. With land cover, they're trying to store the land cover that takes up most of that cell. Since we're dealing with cells, we're not going to get precise unless we make our cells really, really small. All right? Okay, so the key to understanding is both the values in the cell and then what the function does, so that way we understand what the outputs are doing. So most operators that we've discussed so far, all the ones we talked about last week, are what we call local functions. They use only the data at one input point to determine the value at an output location. So that's what a local function is. So we're going to talk about some more local functions. We talked about basic mathematical local functions last week. But to give you a preview of where we're going, we're going to talk about all these different types. We've got local functions. Those are performed one location at a time. We've got focal functions, which are concerned with the neighborhood of values. Zonal functions. Zonal functions are probably the thing that is most similar to doing an overlay and then a dissolve. So when we do, if you're familiar with vector GIS operations, we do an overlay and a dissolve. We're trying to answer the question like, what is the total, what is the average elevation within a city? That would be a zonal operation. What is the total population? Like, let's say if we had a raster that represented population, where each cell told us how many people lived in each cell. Another zonal operation would be what's the total population in a certain area. That would be another zonal population. And then finally, global operations are operations that that take into consideration the entire set of values, and they're basically just modified zonal operations. So when I said 3 or 4, a zonal operation and a global operation are really the same thing, where the global operation, the zone is the entire area. We'll talk about this a little bit more next week. Now, speaking of overlay, I told you that zonal was kind of like overlay, but what if we just want to do an overlay in GIS? Well, if we just want to do an overlay in raster GIS operations, it's really a local operation. In other words, we're going cell by cell and doing an operation. So one thing that we could do is in vector GIS, we call an intersection where all polygon parts occur in both A and B, right? So this is a little bit of a review. You probably should have learned this even in an introductory GIS class. A union is where the results include all polygons that occur in either A or B. And then these are less common, but we might have a not and an exclusive where we're basically trying to find out the differences. We can do these in raster GIS, but we have to think a little bit more about how they're done. Okay, so here's where I plan to do some demonstrations, both here. Well, I'll do the next slide before I get to that. All right, proximity analysis is also something that you probably did in your vector analysis class. So we need to think about how we did it. Well, we did a buffer of an area, and that gives us a new polygon where everything is within a certain distance of an input data set, right? So how do we do this in raster? Well, in raster, there's a distance operation. The output is that each cell represents the shortest distance back to the value in the layer. Right? So the output, every cell gets a value. It's also a local operation. Every cell gets a value, and that value represents its distance to a particular location. All right, so let's do a little bit of demonstration here at this point. So I'm going to open up ArcGIS Pro. Then we'll take a little bit. I'll take a little break so I can stop the video and make sure it records, and then we will meet back up. So I got to sign in. Did you, Roy? Were you able to accept that invitation? All right. Really quickly, I'll see what happened. Just in case. Yep. Okay. There you go. So I need to enable ESRI access. Okay, I think you should be able to log in. Why don't you try to log into ArcGIS Pro? Make sure that works. You should be set. Okay, so I'm in. Here's my project from last week. I'm gonna do the demonstrations from the project that I made last week. If you're following along, you can simply create a new project and add the Laguna Beach data in. That's what I'm going to demonstrate with. Yeah, hitting a blank one will be fine if you're following along. In Canvas? Oh, so you don't have the data. Let me take a look. Okay, that's the data for this week. That's not the data I'm going to use right now, but we could. Okay, but we can use that. So the problem is it doesn't appear over here. Okay, so right click on data. Yeah. Is that where you put it? Yeah. Let me see where you put it again. Make sure. Go into it. Yeah, right click on that. And then go right here. Just click it. And then right click. And then go back to it. Don't go. Where is it?
It's on the left one, I think. Or no, it's Laguna Beach.
I didn't. Sorry. I'm in a message. Okay. That's great. So we'll hit add data. Not right now for these examples. That's okay. We will go over that. You tried to log in with our You did. On this guy.
It does have a W. Yeah.
Let me see for a second.
Honestly, I probably
like
won't.
apples.
I probably won't. That's why I don't learn. Because I have no experience.
So you are signed in here. Okay. Go back to ArcGIS Pro. So it takes spaces. That's the same way you logged in here. Let me look and see if there's something that I need to change on there. User, that's fine. Okay, there was one more step. So there's like 3 steps to give you everything that you need. So now try it. Did that work, Roy? Okay. Okay, so I've got this old one up. What I'm going to do, rather than mess with the data that's already here, is I'm just going to insert a new map. Like I told you last week, ArcGIS Pro is map-based. So I can hit Insert New Map, and I can just create a new map. I can have more than one map open, right? So if I go to the catalog pane over here, which, by the way, you get to by going View, Catalog pane. That's how I get to it. Then I can see the data sets. I've already added the Laguna Beach data set here, but if you haven't, then you could just hit right-click here and say Add Database, and then you would have these data right here. Okay. All right, so we're going to talk a little bit about overlay, because overlay just by itself is a little bit complicated to think about mathematically in the raster data format. Okay, so let's say, for example, a common overlay operation might be that we want to find out all of the values for a certain land cover. So I'm going to throw land cover in there. let's say we want to find all of the scrub shrub land cover that's above a certain elevation, because those those areas are going to be more susceptible to fire, because the water runs off of them quickly. Okay. So these areas that are scrub shrub, which is a drier biological type, are going to be more susceptible to fire when they're up high on the ridge lines. Okay. So we're going to ask that question. That's the question we're trying to find out. So we need to find out what areas are both vegetation, A, and they're high in elevation. They meet two criteria. So if these were both vector polygon layers, we could do what type of overlay from learning about maybe in a GIS course. Or it's on that slide I just showed. When we're doing an AND operation between two layers, we're trying to find out if this is true and this is true. Yeah, it is a logical operation, right? Yes, it's an intersection. So it's an AND operation, trying to find out if two things are true. It's an AND operation. So how do we implement that in a GIS? Well, exactly what Elvis just said. It's a logic operation. We could do it logically. Okay? We could do it all in one expression in map algebra, or we can run the individual tools that build up to it. But that's how we implement a overlay, which we think of as an overlay operation. So we have to decide, though, all sorts of things. Well, not all sorts of things, but there's a few things we have to decide. One thing is that we have to decide what do we want our output to look like. You know, the simplest way to do this is to say, okay, well, we want everything that meets both of our criteria to be 1, and everything that doesn't represent both of our criteria to be 0. Okay. Now, there are reasons to choose different values, and we'll talk about an operator that allows us to choose any operator out there. But for now, we can just do the simple logical operations. An intersect is the same thing as an AND operation. And so we need an equation that says, what does our equation need to look like so that we'll have blah, blah, blah equals, and we'll have an output data set of 1s and 0s. Let's think about what that equation needs to look like. Okay. So what are our inputs going to be for that equation? Oh, by the way, Roy, did it work? Okay, good. All right, so what are our inputs going to be for that equation? So our output's going to be 1s and 0s. Let's not even think about, though, at this point, 1s and 0s. What are our inputs going to be if we're asking the question, we want to find scrub-shrub areas, and so they have to be scrub-shrub, and the elevation has to be high. Let's just say high is 150 feet. I think we're doing feet, right? No, we're doing meters. So 150, let's just say 150 meters. Okay? Right, land cover and elevation are our data sets. So I'm going to go ahead and add both of those data sets. So here we've got land cover and where'd the elevation go? Elevation. So those are our elevation data sets. Now they have different resolutions. So for now, let's let ESRI handle, because they almost have the same extent. Okay, we're going to let ESRI handle what's going to happen. I'll just tell you what's going to happen. It's going to, by default, choose the maximum cell size, which is fine because we can't really get any more precise than the maximum cell size. But if for some reason you wanted to keep the original data set, you could. Okay. All right. So you just have to set that, and I'll show you where you set it. Okay. So let's think about this data set. We already did that last week, right? We already did the data set last week where we said, okay, let's find the areas that are above 150 meters. So I'm going to just go ahead and do that. There's a few different ways we could do it. Right? This is the toolbox. Sorry, this is this is the way you can find the tools. It's under favorites. You can find any tool you want. It'll also show you the last 5 or 6 tools that you've ran. If you want to just look at all the tools, it's under toolboxes here. These are all the tools that exist. So it is a logical operator. So if we go down to spatial analysis tools and choose I think it's under local, right? No, not local. We are going to talk about some of those today. I'll just search. So we got the AND operator. It'll tell me where it is. Boolean AND. That's under an image. There's Boolean AND. So Boolean AND is under math. It is under logical, but it's under math then logical. That's why I didn't find it. Okay, so that's how we would do. That's why we'll combine the two. But first, we need to do a greater than, which is also here under logical. We get our greater than. This will tell us our high areas. When we're just running any tool in ArcGIS, I'll wait for this to come up for a second. We've got this other window. Did I talk about that a little bit last week? The environments window? Okay, so the environments window is where we could set the output cell size. We could also set the output snap raster extent. I remember I did talk about the snap raster last week. Okay, great. So by default, notice that the cell size is maximum of inputs, which is what I said. So first, though, let's just do greater than, and say this is very similar to what we did last week. Elevation greater than 150, and our output we're going to call it high places. And we'll run that. So there are all high places. So let's do the next step in our equation is that we need to do what? Well, let's think about it. Let's go back to this. How are we going to extract? How are we going to create a data set that shows us just where the scrub shrub, because that's what we're concerned with. How are we going to create a data set that shows us just where the scrub shrub is?
We need the number that represents scrub shrub.
Yeah, we need the number that represents scrub shrub, and then there's probably a equal to, right? There's an equal to right here. What number is scrub shrub?
12.
How did you get 12, Dan?
I clicked on a scrub shrub pixel.
That's a good way to do it. So Dan clicked on a scrub shrub pixel and it tells us what the number is. Remember, it's always a number. So let's do equal to, and then choose the land cover data set, and then choose 12, and then we can call this output scrub shrub. And let's think about once it runs, let's think about the output. So what do the values in this output data set tell us? What are the output values? Let's go to the legend to see. Because we could just say, oh, they're like ugly green and blue. So the ugly green areas are what? They're 0, and so they mean not. And then the blue areas are 1, and so they represent true. They are scrub shrub. So finally, if we want to find out what values are scrub shrub and our high places, which is this one, how do we do that? What mathematical operation could we do to identify those areas? Is there a simple math operation that would allow us to identify all those areas? I don't care what the numbers are at this point. I just want to be able to have one value that shows the areas that don't meet the criteria and another value that does represent the areas that do match the criteria. And these are our two inputs, scrub shrub and high places. It's all zeros and ones, right? So can you think of, it can be a logical operator or it can be a math operator, which really is a logical operator. Yeah, we could. I think there is an AND operation. Let's look here. There's a Boolean AND operation. Okay. So let's do scrub shrub and high places. And we'll call this burn regions, maybe. Or watch burn regions. So run this, see what we get. All right. Do we think that matches the criteria? Is that the right areas? Are those the right areas? So there's. Yep. I think they do. Okay. Some people, you might be wondering, okay, well, why doesn't it look like these smoother boundaries than these smoother boundaries? Why do you think that is? What's that? Yeah, so we started with the land cover. Did you guys have a comment down there in Hattiesburg?
That is restricted by the cell size of the.
Right, exactly. If I was to rerun this Boolean AND, go under environments and choose minimum of inputs and rerun this, of course, it never works the way it's supposed to work, but it should produce the right answer. Yeah. So now we get some of these areas. Now you see that we don't get smooth areas everywhere. Why? Well, because these areas were totally within or totally restricted by those areas. So there wasn't a smooth boundary there. But the cell size on this data set is much larger. Much smaller, so the data set itself is larger. Anyway, I would recommend in this case, personally, to leave it at the maximum of inputs. That's the default. All right. Okay. There is another way to do the same thing, right? So when we already have zeros and ones, mathematically we could have just multiplied these two data sets together, 0, 1, 0, 1, and we would have gotten what? We would have gotten the same answer, because a 0 times 0 is a 0. 0 times a 1. There's a few other tricks for doing this. Okay. Oh, actually, I'm going to leave that there. What if we add them? Go back and just do a mathematical addition. Plus is what it's called. What if we added these two data sets, the scrub shrub and the high places? I'm not going to even be concerned with what I'm going to call it. Just hit run. So now we have three different values there. What does the dark pink area that has 2? What is that? What does that represent? What does a 2 here mean? If you were to say it in plain English, what does a 2 represent? Yes.
The shrub and the elevation.
Right.
The proper elevation.
So it's scrub shrub and the high elevation together. they're occurring concurrently. What does a 1 mean in this case? Yeah. Do we know which one? Just by looking? No, we don't. So we know that it's either high elevation or scrub shrub. So this is actually like the effect of a union. A union is like if in GIS doing a union would be that well, basically everything that's a reddish color. So the dark red and the two values together would be the effect of a union. In other words, saying if either of these two things is true, show me all those areas. And that would be both of these. But yeah, the red is only one or the other true. And then finally, the purple is neither is true. It's neither one of those. All right. Okay, so in the old days, like when those articles were written, there weren't necessarily some of these more advanced tools. And so let's say we wanted to find out for sure all the different combinations. Well, one thing that we could do is to take the scrub shrub level. I'm going to go to scrub shrub, and I'm going to add 10 to the scrub shrub value. I just added 10 to scrub shrub, and I'll call this scrub plus 10. Or sorry, P10. And run that. So now I got 10 and 11 instead of 0 and 1. Then I'm going to take this scrub plus 10, and I'm going to take the original high places. So this is the high places, zeros and ones. And I'm going to add those two together and call it scrub high overlay. And run that. Now you'll see I have 3 different values. Okay. Interestingly, I only have 3 different values, but there's actually 4 different values that would be possible. Okay, what other value should show up there, but doesn't because there are no areas that are not high. Okay, actually, let's just go through and see what each of these means. What does 1, 0 mean? It means that we've got a 1 in which of these two overlays? This one or this one? It's always a 1, actually. What happens if we got, what I'm trying to say is, what happens if we got a 0 in both data sets? What should the output be? A 0 in both data sets. The output should be 10, right? Because 10 plus 0 is 10, right? What if we got a 1 in both data sets? What should the output be? Yep. And no, if we got a 1 in both data sets, we should get a 1 and a 1, right? Or a 1. Actually, I think I messed up a little bit, right? No. A 0 plus a 0 would be a 0 plus a 10 would be a 10. A 10 plus a 1 would be 11. An 11 plus a 0 would also be 11. So anyway, I messed up. I'm trying to find out a way to get all of them unique, to get a bunch of unique values, right? Because there is a way to do it.
So you're not guessing which, if it's either or, so you
Right.
know which one is which. Okay.
Exactly. So there's 2 different ways to get an 11 now, right? An 11 plus a 0
Or a 10 plus a 1.
or a 10 plus a 1. So there is a way to make it unique, and you need to think about the formula. But nowadays, there's actually a way to do these more complex overlays. When I say nowadays, it's been around for a long time, but previously you really had to think about how, and you still kind of do a little bit, but if we go back to geoprocessing, analysis. I lost my toolbox. I think I closed it. If we go back up here, there's a whole overlay box now. If we go to the overlay box and we expand it, okay, then we can do something like locate regions, okay, or weighted overlay. Overlay several rasters using a common measurement scale, or weighted sum. That's actually, I do want to talk about those in a bit, but those are all ways that we could do other types of overlay. Okay. So we followed the formula. Let's really quickly, before we take a break, let's input this all as a single formula. Not the more complex stuff I talked about, but this data set right here. This data set right here. When we created that by doing basically 3 different operations. We did an equal to with the scrub shrub. We did a greater than with the high places. And we did an AND operation to create the final output. So we could do this all as a single operation by doing something like this. So this would be a simple process. So we take the land cover and we say land cover equals, was it 12 or 13? It was 12, right? 12. Lots of times in math we need to put operators here. And then say and. Go slow here. Logical. Oh, it's Boolean. It's Boolean. I forget whether it's typed out and or if it's the double ands. There it is. And elevation greater than 150. So we're doing 3 operations there, and we'll call this slash watch burn 2 and run it. And then we should get the same exact answer. Yep, we get the same exact answer, but we've built it as a single equation. So whenever we have a particular answer, whenever we have a particular thing that we're trying to model, we need to come up with the equation that will help us to get there. Okay. Yeah. Yeah, so you could double click on land cover, or you could type in quote land cover. But yeah, equal. There's 2 equal signs. There's a space and a 12. And then there should be a space here as well, and a space there, space. And then it should run. Okay. All right. So the other thing that I wanted to demonstrate, that I wanted to talk about, is this distance operation. We're going to talk about a few of these others as we go in the class, but you feel free to explore the other ones. We're going to start with this Euclidean distance. Okay. Let's look at the help for this, because it's always nice to look at the help and see what it's doing. There's always, in the help, there's always a a summary of what's happening. Okay? It calculates for each cell the Euclidean distance to the closest source. Okay? So if we had a raster data set that looked like this, that had ones here, a bunch of no data values, and twos here, and we ran the Euclidean distance tool on this, this would be the output. Where the output would tell us the distance back to a source. So in other words, this value is 0. It's 0 because the distance back to a source is 0. Okay? This cell here is a value of 1. Here, I'll put this on here. Oh, let me make this bigger. Oh yeah, that's better. This value here is 1. Why is that value 1? This value is 0. It's 1 unit away from this cell. So a little bit more complex question. Why is this one 1.4?
Close to the ones kind of, but right next to the two. Maybe that evens it out to a 1.4.
Yeah, so it's actually, exactly, it's using math, so it's a little bit further. This is a little bit further. In fact, that distance is 1 squared plus 1 squared, okay? And then we take the square root of 1 squared plus 1 squared, which is 2 squared. And so that value is 1 point, it's a what do they call that, irrational number? I'm not a math whiz or anything, but you know, the number that just keeps repeating. It's this value, square root of 2. It's that number. So rounded to 1 decimal place, it's like that. What if the cell size was 10? Well, it would just be 10 times this number. If the cell size was 20, it'd be 20 times that number. If it was 40, if it was 100, yeah.
So that 1.4, is that also taking into account how close it is to the 1 as well? Whenever it gives you that distance?
No, it's only the distance to the source. So it's the center of this cell to the center of this cell as the crow flies. Well, the quickest distance back. Now, what about this one that says 2? Why is that one 2? Well, remember, if we look at the description, it says it calculates the distance, the Euclidean distance to the closest source. So here, 2 is actually closer to this cell, that's this cell we're talking about, 1, 2 back to that cell, versus to this cell, it would be 1.4 plus 1.4. Well, I haven't played a whole lot of Minesweeper, but
Like the bomb is here and they don't have a 1, and that means the bomb is like goes before you go out. It's like 2, 3. You know how many squares to the bomb?
I guess in some way it's related to Minesweeper. Yeah, the value. It's important to understand the output value, and the value here is just the value back to the closest cell. Okay. Closest cell. Now, what if we just wanted to know the value back to here, to the ones? We could pre-process our data, right? What could we do to pre-process our data to do that? To get rid of the 2s. Using like a logical operator. If we wanted to find out, we already did this with the scrub shrub, so it's just a modification of that. So instead of just land cover, we want just scrub shrub. How did we do that? Yeah, we used the value and we did the equal operation. Okay? So that's how we would do it. We'd say equals 1, then we'd run that and we'd get a data set that looked just like this, except for this would be a 0. And then we'd run the Euclidean distance and it would only give us the distance back to there. Let's try that really quick. So here we have our scrub shrub data set that we've already created. Okay, so let's calculate what's the distance to the scrub shrub in every single cell. We just want to know how far we are from scrub shrub in every cell. So we could do that by taking the scrub shrub data set and saying that we want to find out, by the way, we can specify the output cell size, but it's by default, it's going to choose the input cell size. Okay? So now every cell will tell us the distance back to scrub shrub. We run this. Actually, it might have to be no data, not 0. Yeah, okay. So sorry, we need one other step. Everything's 0. So we haven't really talked about this yet, but we do talk about this in the slides. How do we change the 0 values to no data? That's a question. So there's a tool just for doing that, okay? And that tool is called set null. So if you type in, I don't know where it is, so I'm going to search for it. The set null tool is, I thought it was going to show me where it is. Oh, there. So set null is under conditional set null. So set null is basically like the equals tool, but it sets everything that's not equal to the value, that's equal to the value you're looking for. It sets it equal to 0. I mean to no data. Here, let's look at what this is. Okay, so this is the function. So the function for set null takes, well, in this case, it takes a value and another value and finds anything where it's equal to 4, and that is going to be no data in the output data set. So 4 becomes no data. We want it to do it so that 0 becomes no data. That's what we want. All right, so let's look at this here. So we have a conditional raster. So we can do something. Okay, let's do this. Here's my conditional raster. It's the scrub shrub data set. Okay. So input false raster or constant value. That's the data set that's going to be the expression. Here's the expression. So the expression that we want to do is say if it's equal to 0, add. This here, this data set here is actually the value to get if it's not going to be set null. In other words, the tool will do some things that are a little bit more complicated than the way I described it at first. So what this is doing is saying, if scrub shrub is equal to 0, make it null. If it's not equal to 0, make it this data set. So in order to just set this up exactly the way we'd want it to do, we would say, if scrub shrub is equal to 0, make it equal to null. If it's not equal to 0, make it equal to the original data set. Yeah. What's that? Oh, yeah, sorry. Thank you. Add clause needs to be value equal to 0. And then this would be the original data set, the scrub shrub data set. So basically what this would allow us to do is we could skip the step of making the 0 and 1 data set. How would we do that? Well, if we said, if land cover is equal to 12, set it, does not equal 12, set it to null, else set it to 1. We could skip that step. But this will work too. So now we're going to run this, and we should get a bunch of no data values, which we do. I'll turn off this other data set. These other data sets. All the other data sets, except for the topographic. So now I just have that last data set on. And that is just the land cover equal to scrub shrub, and everything else is no data. So now we can go do the Euclidean distance. Euclidean distance. So I'm going to choose the, I didn't call it anything good, which isn't bad. So now I'm going to add, I'm going to call this distance SS for scrub shrub. Now this is actually a newer thing. I think it's only in ArcGIS Pro. It might be in the latest versions of ArcMap, but it's a relatively newer option. So most of the distance operations now in ArcGIS allow you to choose between planar distance and geodesic distance. And what I've described to you already is planar distance. In other words, the distance from the center of this cell to the center of this cell. Okay? With geodesic distance, it actually calculates the distance on the curvature of the Earth. Now, in an area this small, it doesn't really matter. It's probably just going to add processing time to choose geodesic. But let's say you were trying to do this for a larger area that represented like half of the Atlantic Basin or something. Then you definitely want to choose geodesic because the distance would be different traveling over the curvature of the Earth rather than from the center of the cell to the center of the cell. So basically, it does a lot more calculations to do that, and so but it's more accurate, especially for an area that covers a larger geographic extent. If it covers a small geographic extent, there's actually more elevation difference here than there is curvature of the Earth difference. So you're not really adding any benefit by choosing geodesic in such a small area where there's actually other things that are causing it to mess up more than the geodesic versus planar calculation. But that's what that does. So I'm going to run it, and now what do the values in this cell mean? Sorry, what do the values in the output cell mean? What are we got the highest value is 1006. So what does that mean when I go down here and I get a value, I click this value right here and I get a value of 1006.23. What's that mean? What does that mean for that cell? From the nearest what? From the nearest scrub shrub. Okay. So if for whatever reason I wanted to be really far away from scrub shrubs, this would be the furthest away I could get from a scrub shrub area. All right. That's the distance, the Euclidean distance operator. So we're going to use those. Today we're not going to use set null a whole lot because we're actually going to start in a different place. But we're going to use set nulls a lot. We're going to use proximity operators, Euclidean distance, and we're going to use basic logical operations in the lab that we're going to do today. All right. So we're going to take a little break right here. And there is one more thing I want to show, but I'll do it in the second half of class. We'll take a little break, a 10-minute break. Actually, let's do a 15-minute break. Come back at 3:05. And then there's one more concept that we need to go over before we do the lab. And then we'll introduce the lab, and that'll be it for today. So I'm going to stop this. 1 hour and 20 minutes. That's good. That's about how long.